So hello everyone, welcome you all to live session 6 of NPTEL course Fluid Flow Operations taught by Professor Shubhada Kumar Majumdar. My name is Nagapani Sai Kumar and I'm the distinguished for this course. So last week we had a detailed discussion about the flow of viscous fluids, okay? And this week we'll be studying about or we'll be discussing about different losses in pipes, which basically includes different equations to calculate friction factors and also to calculate how much friction how much amount of energy is lost because of the frictional effects. Okay, we'll also be looking at a couple of equations as well, like Darcy equations, okay, and planning friction as well. So, last week when we were discussing about flow of viscous fluids, we discussed that an ideal fluid is a non-viscous fluid, and also uh, the nature of non-ideal fluid is such that there will be no viscosity, right? So, but in nature or in practical case, we don't have anything called ideal fluid which is having zero viscosity, right? Each and every fluid which is existing in nature has a certain viscosity value, right? So, for this reason, like the fluids which are having no, which are considered or which are assumed to have zero viscosity are called ideal fluids, and all other fluids are considered as practical or real fluids. Okay, so when there is viscosity or viscosity is a kind of opposite force which will be acting for the flow. Like whenever a fluid is flowing, the viscosity will always be acting in opposite direction. Okay, so it will try to stop the fluid. So in order for the fluid to flow continuously, there has to be a continuous supply of energy which is required to overcome this shearing resistance. Okay, so let's because of this, let's say if you're supplying E amount of energy, there will always be a certain amount of energy which is lost. Let's say it is capital small e. So let's find out what are these different losses that will be existing in a pipe. Okay. So fluid frictional resistance, whenever there is a so fluid resists objects due to the friction acts on the body that are moving through the fluid. Okay. So there will always be friction between the surface of any body or pipe and the fluid that is flowing. Okay. There will always be friction. So fluid friction takes place between layers within the fluid that is moving relative to each other. This internal resistance to flow is named by viscosity. Okay. So apart from this viscosity, which is between liquid layer and the surface of the body, there is also one more viscosity which is considered as internal viscosity because this is within the liquid. So we have different layers of liquid, right? Okay. So within these layers of liquid also we'll be having this frictional force. Okay, whenever because they'll be flowing, right? So between these layers we'll be having frictional force, and this is considered as internal because it is happening within the liquid, right? So this is called as viscosity. Okay, this internal resistance is called viscosity. So fluid viscosity measures its resistance to shearing action between these fluid layers. Okay, so how much resistance is being applied between these layers. So these forces depend upon the velocity between layers in the fluid. Okay, so it is proportional to the or it is dependent on the viscosity is dependent upon the velocity between the layers. Okay, so du by dx. Okay, so it is a function of change in velocity with distance. Okay, so frictional losses. During frictional losses through the conduct, the energy is lost due to the frictional resistance. This is called frictional loss. So as I've told you, this is considered as external resistance or yeah, external resistance. So in laminar flow, losses are proportional to the fluid velocity. So when you're considering a laminar flow, so these frictional losses will be proportional to the velocity. But whereas in turbulent flow, it will be proportional to the square of the velocity, fluid velocity. Okay. In turbulent flow, so as I've told you, in turbulent flow, losses are proportional to the square of the fluid velocity. The friction losses can be quantified by the loss of pressure or head. Okay, so we already discussed about head, right? So it can be this loss can be quantified in terms of loss of pressure or loss of head that occurs in a pipe or duct flow due to the effect of fluid's viscosity near the surface of the pipe. Okay, so let's frictional resistance law. It is in laminar flow. So this is also called Da Vinci-Westberg or unfanning friction. So we'll use these equations to calculate this frictional resistance. Darcy is fanning equations. Okay. So Bernoulli has already given an equation which relates or which formulates relation between changes in total energy of the fluid to energy dissipation, right? Okay. So this energy dissipation can be expressed in terms of head loss or specific energy loss. Okay, so head loss can be it can be expressed in head loss, that is HF, or it can be given in terms of specific energy loss, that is GHF. This is in joule per kg. So according to Bernoulli's principle, we already have U1 square. Let's say if you are let's take a fluid flow in a pipe. Okay, so let's say here we are having this is H1 and this is H2. This is a liquid level. Okay, and U1 is equal to U is equal to U2. So that means velocities are different, are same at both these locations, and these are separated by distance of L. Okay, and the height difference. Let me redraw it again. This is H1 and this is H2, and they are separated by distance of L. And velocity is same at both these locations. Okay, so let's say the distance or height difference between H1 and H2 is given by HF. Okay, so if you apply Bernoulli's equation both these places, we will get U1 square by 2G plus P1 by rho G plus Z1 will be equal to U2 square by 2G plus P2 by rho G plus Z2 plus HF. Okay, so let's say this is H1, this is like the total head, and this is H2, that is total head at location 2. Okay, so if you observe this diagram, so the velocity is same at both these locations, right? But there is a difference between water level in case 1 and case 2. Okay, so this is because there is some loss in energy because of some reason. Okay, so that loss in energy is because of the frictional force. Okay, which will be representing here as head loss. Okay, so we'll be representing it as HF. Okay, so let's take a case where in this case Z1 will be equal to Z2, right? So that means they are at the same elevation. Okay, so there is no height difference, and also U1 is equal to U2. Okay, as we have mentioned, both velocities are same. So, and also the pipe is of uniform cross section and it's a perfectly horizontal pipe. So in this case, so for uniform cross section and horizontal pipe. So in this case, HF will become, that is head loss will become P1 minus P2 by rho G, because both velocities are same, they are at same elevation. So Z1 and Z2 will also be equal. So we'll be left with pressure difference, that is P1 minus P2. So this will give us delta PF by rho G. Okay. So let's say if tau naught is the wall shear stress, so it can be obtained from pressure drop by using force balance. So tau naught will be equal to, let's say if tau naught is the wall shear stress, so tau naught will be equal to frictional force divided by surface area. Okay. So this will give us P1 minus P2 into pi by 4 d square by here surface area will be changing, so it is depending upon the, so it depends upon the contact area, right? So it will be pi d, that is the circumference, and into length. Okay, so it will give us the surface contact surface area. Okay, so this will become d by 4 into del pf by l. Okay, so let's also give equation number. So let's say this is equation 1. Okay, and let's say this is equation 2, and this becomes equation number 3. Okay, so now from equations 2 and 3, what are the equations 2 and 3? So from this equation and from this equation, so we can write, let me write down equation 2 and 3 again. So HF is equal to del PF by rho G. Del PF by rho G, this is equation number 2. And we have tau naught is equal to D by 4 into del PF by rho G. Okay, this is equation number 3. So if you divide or substitute del PF by rho G as HF using equation 2 and 3, then we can write 4 tau naught. Okay, so this will go the other side, 4 will go the other side, then it will become HF into rho G D by L. Okay, so that is the equation. This is L. Okay, so just divide 2 and 3, you will get this equation. Okay, so now let's say this is equation 4. So now let's divide both these equations by rho v square by 2. Then we'll have 4 tau naught by rho u square by 2. So this is basically velocity. Rho u bar square by 2 is equal to Fd. Okay, so we'll come to this later. Fd, and this is equal to hf into rho g d by L into rho u square by 2. Okay, let's say this is equation number 5. Okay, so this hf is called Darcy, or let me write this equation again. Hf is equal to Fd into L u bar square by 2g d. Okay, so this equation is called Darcy Weisbach equation. Okay, so we have one more form as well for this equation. So this can also be written as del Pf is equal to half into Fd into rho u bar square into L by d. So just substitute Hf is equal to del P by rho g, and you will be getting this equation. So this is equation number 7. This is 6. Okay, this is also Darcy equation. Okay, so this equation number 6 can be further expressed as Hf is equal to 4 Ff into L u bar square by 2gd. Okay, and similarly del Pf will be equal to 2Ff into rho u bar square into L by d. Okay, so this is called fanning equation, and here Ff denotes fanning friction factor. Okay, so always remember fanning friction factor will be 1/4 of the Darcy friction factor, that is Ft. Okay, so this is called Darcy friction factor, and this is fanning friction factor. So Ff will always be equal to 1 by 4 of Fd, which is a function of Reynolds number and epsilon by d. Okay, so let's take an example. Let's say that water is flowing through a 100-meter. Let me write down the equation, or let me write down the question. Water is flowing through a 10-meter long circular pipe of diameter 0.05 meters at an average velocity of 2.5 meter per second. So determine the head loss, frictional pressure drop, and shear stress. So we are already given that Darcy friction factor is 0.115. So how do you calculate this? We are supposed to calculate the head loss. So head loss is given by HF, which is equal to FD into L U bar square by 2GD. Okay. So we are already given all the values. We were given average velocity, that is 2.5. U is given, and the length L is also given. So L is equal to 10 meters. U is equal to 2.5 meter per second, and diameter is also given, that is zero point zero 0.05 meters. Okay, so and FD is also given, that is 0.115. So FD is given, L is given, U is given, two constant, D is given, and G is also and G can be taken as 9.8 meter square per second. Or you can also take 10 if that suits the calculation. So you can take 9.8 or 10 depending upon your calculation simplicity. So if you solve this correctly, you should be getting around 7.36 meters. Okay. And we are also asked to calculate fractional pressure drop, right? So how do you calculate it? So just substitute value for HF. So HF is del P. So if you substitute HF here in this equation, you'll be getting PF. So what is the equation for PF? Yeah, in terms of Daniel's friction factor, PF can be written as PF can be written by using equation 7. Okay, so I'll write down the equation PF by, okay, so PF is equal to half FD into rho U square into L by D. Again, all the values are given. So if you substitute it, you'll be getting 722, 7221.04. Okay. So cross check these calculations. And we're also asked to calculate tau naught, right? So tau naught again. So tau naught, if you substitute this from equation 4, we can calculate tau naught. Okay. Oh, sorry, you can also calculate it from equation 3. Okay. Tau naught is equal to d by 4 into delta pf by L. Okay. So what is the equation? D by 4 into delta pf by or del p by L. Okay. So if you substitute the values and solve the equation, you'll getting tau naught as 90.23 or 26 Newton per meter square. Okay. So all the values are given. We just have to substitute them and simplify it. Okay. So now there's something called universal friction factor. So let's see this for laminar case. Universal friction factor. So we know for laminar flow, mean velocity can be calculated as this was discussed long back. Okay, so for laminar flow, mean velocity can be written as R naught square by 8 mu into dp by dx. So this was discussed long back. Okay, so I'm just directly writing the equation. So this can also be written as d square by 32 mu into del p by L. Okay, so let's say this is equation 11. So from equations, let's say this is 7, this is 8, and this is 9. Okay, so from equation, and this becomes equation number 10. So from equation 9 and 11, we can write from 9 and 11, we can write FF as phase fanning fixture as 16 by rho u bar d by mu. This will become 16 by RE. So we have F right. So we can also write in terms of FD as well. So FD will be equal to 4 times of FF, right? So it will be 64 by rho u bar d by mu, which will be equal to 64 by R E. Okay. And for turbulent flow, So as per equation number 5, okay, as per this equation, FD will be equal to 4 tau naught by 4 tau naught by rho u bar square by 2. So let's say this is equation number 14. Okay, and for turbulent flow, V star will be square root of tau naught by rho. So let's say equation 15. So equation 14 can be written as V star is equal to u bar into square root of FD by 8. Let's say equation 16. This is equation number 16. Okay. So let's see the case for turbulent flow through smooth pipe. So for turbulent flow through smooth round pipe, the average velocity can be given by. So as is a turbulent flow, we'll be dealing with V star. So it can be given by V by V star smooth will be equal to 1.75. This also we discussed last time. 1.75 plus 2.5 into ln rho V star R by mu. Let's say this is equation number 17. So if you substitute shear viscosity, that is, sorry, shear velocity, that is V star from equation 16, from this equation, and substitute in equation 17, we can get, so we'll get 1 by square root of FD by 8 is equal to 1.75 plus 2.5 into ln rho u square, rho bar, rho into u bar by mu into square root of ft by 8 into d by 2. So let's say this is equation 18. And if we further simplify this, we'll be getting 1 by square root of fd is equal to minus 0.913 plus 0.884 into ln re root ft. So this is applicable for laminar sublayer thickness of laminar sublayer greater than 1.7 into epsilon. This is only applicable at this region. So let's take one more example. So let's take the same example as earlier. So, but let's say this time the velocity is a turbulent velocity. It is in turbulent condition. So let's write down the question again. Water is flowing through 10-meter long circular smooth pipe. Okay. So L is equal to 10 meters smooth pipe, smooth circular pipe. Okay. And diameter diameter is given as 0.05 meter. Okay. And the fluid inside this circular pipe, it is flowing at a average velocity of 3.7. Okay, so this is a circular pipe. Its length L is equal to 10 meters. Sorry, this length L is equal to 10 meters. Diameter is equal to 0.05 meters. And velocity or mean velocity or average velocity is given as 3.076 meter per second. Okay, so we are asked to calculate shear velocity and Darcy friction factor. Okay, so we are supposed to calculate V star, that is shear velocity, and FD, that is Darcy friction factor. So let's use the same equations. So V by V star is equal to 1.75 is for turbulent flow, and flow is in within a smooth circular pipe. So let's use the same equation. V by V star smooth will be equal to 1.75 plus 2.5 into ln rho V star R by mu. Okay, so V is given, that is this is also dependent as V. Okay, so V is given as 3.076 by V star, which is equal to 1.75 plus 2.5 into ln. What is the so here water is flowing, so that means rho will be equal to 1000 kg per meter cube, and also viscosity will be 0.001 for water. So just substitute them. It will be 1000 into V star into radius, that is half of diameter. Okay, so it will be 0.025 by 0.001. So if you simplify this, V star will be around 0.139 meter per second. And we are also asked to calculate Darcy friction factor, right? So how do you calculate it? So using this equation. So we'll get 1 by square root of FD is equal to minus 0.913 plus 0.884 ln RE square root RE into square root of FD. So here we have to use trial and error method, because sorry, we have to use trial and error method to check which would be the correct answer. Okay, so if you do the trial and error method, we'll be getting FD as 0.01646. So this is by trial and error method. You can use Newton-Raphson method as well. Okay, so this is how we'll be able to solve this problem. Okay, so do you have any doubts in this? If this is clear, we'll move on to the next one. That is, so now we discussed about friction factor in turbulent flow for a smooth pipe, right? So let's see the case for rough pipe. So firstly, if you are changing the surface of the pipe, that is, if you're changing from a smooth pipe to rough pipe, the relation of the equation for shear viscosity, shear velocity will also be changing, right? So let's first write it down. Through rough pipe. Okay. So for turbulent flow, through a rough round pipe, the average velocity will be given by V by V star. Rough will be equal to 4.75 plus 2.5 into ln R by epsilon. Okay. R by epsilon. So this is equation 19. So now substitute V star from equation 16. So if you substitute and if you simplify the equation, you'll be getting 1 by square root of fd by 8 will be equal to 4.75 plus 2.5 into ln R by epsilon. Or let's say you can also write 1 by square root of fd will be equal to 1.066 plus 0.884 ln d by epsilon. So let's say this is equation number 20. And this is applicable for delta less than 0.08 epsilon. Okay. So let's also solve the same problem that we just discussed. Let's say all the conditions remains the same. Okay. But instead of smooth pipe, we are having a rough pipe in this condition. Okay. So, so water is flowing. Water is flowing. Average velocity is 3.076 meter per second. Rough pipe. Length is 10 meters. Diameter is 0.05 meters. Okay. So now calculate shear velocity and Darcy friction factor. So we have V by V star rough is equal to 4.75 plus 2.5 into ln R by epsilon. Okay. So using trial and error method, V star will be 0.136 and epsilon will be 0.02 mm. We have to do trial method because we have two variables here. Okay. And using these values, if you solve for FT, it will be 1.066 plus 0.884 into ln d by epsilon. So if you substitute values, FD will be equal to 0.01561. Okay. So the this roughness factor, so like we are saying smooth pipe and rough pipe, right? So this is a relative term and it depends a lot on the material of the pipe. Okay. So for so let's see the values of this roughness for different pipes. Okay. So for asphalt cast iron, these are experimentally determined. Okay. So for asphalt cast iron is 1.2 or 1.12 or 0.120, and for cast iron this is 0.265. For concrete pipes, this is zero point 0.3, and it also varies till 3, 0.3 to 3. And for galvanized iron, 0.15. For PVC, glass, and other drawn tubing, this value is 0.0015. Okay, so it depends on the material of construction. Okay, so let's say you are using a pipeline. Okay, so let's take any material, be it cast iron, asphalt cast iron, or cast iron concrete pipe, whatever it may be. So you have started using a pipeline. So as you use it for a very long time, what happens? The reference will not be same, right? It will be varying, like it will be changing, right? So when you use it for a long period of time, the roughness of the material will be, or roughness of the pipe will be changing. So how do you determine this change in roughness? So you have to know the value of the initial roughness, or roughness of the new pipe. Then you'll be able to calculate the roughness of old pipe. So let's see how to do this. Determination of roughness of old pipe. Okay. So according to Colebrook and White, the roughness height of old pipe can be determined by knowing the roughness height of new pipe based on the age of the pipe. Okay, age of the old pipe. So they determined, or they formulated that E old, okay, will be equal to thickness of roughness, or roughness height for an old pipe will be equal to roughness of new pipe plus alpha T. Okay, so where E old is equivalent roughness height of old pipe, and epsilon nu is equivalent, or let's say roughness, height of old pipe, and T is the number of years of usage, and alpha is constant. So this alpha can be determined experimentally, which varies depending upon the pipe. Varies with pipe material. So let's take an example. So it is observed that high viscous corrosive liquids is flowing through a pipe of roughness 0.08 mm. Okay, so E nu is given as 0.08 mm, and the pipe was kept unused for almost 5 years. So T is 5, and it was found noted that when it was used, the roughness of the pipe was zero point zero 0.01. That is, E old will be zero point zero 0.01 mm. So what should be the roughness of same pipe when it is used after 5 years? Okay, so we are asked to calculate E old after 5 years. So how do you do? First, we have to calculate alpha from this data. Then we'll be able to calculate E old after 5 years. So how do you do it? So this will be 0.01 by 1000. This is in mm, right? Will be equal to 0.08 by 1000 plus alpha into 5 years, right? 5 into 365 days into 24 into 3600. Okay, so alpha will be minus 4.439 into 10 power minus 13. So now we can calculate E new. Okay, so that will be E old minus alpha T. So this will be 0.08 by 1000 minus of minus 4.439 into 10 power minus 13 into 5 into 365 into 24 into 3600. Okay. So if you solve this, we'll be getting 0.00015 meters. That is equivalent to 0.15 mm. Okay. So we have an empirical formula given by Colebrook for calculating friction factor. Colebrook empirical equation for friction factor. So for different conditions, he recommended certain empirical equations. Okay, so let's find out. Let's find out this equation. So for laminar sublayer thickness of 0.08 to 1.7 E, okay, 1 by square root of F will be equal to 1.74 minus 0.868 ln epsilon by R plus 1.18.7 by RE into square root of F. This is equation number 23. This can also be written as 1 by square root of F is equal to minus 0.868 ln epsilon by 3.7 D plus 2.51 by RE into square root of F. This is equation number 24. So he's also mentioned different conditions, right? So this is for laminar boundary layer thickness of 0.08 to 1.7 epsilon. Okay. So then we have Blasius empirical equation. So 1913, Blasius developed an empirical correlation based on experimental work to calculate the friction factor in turbulent flow through a smooth round pipe. So based on his observations, he formulated an empirical correlation, and this looks something like this. The correlation looks something like this. F is equal to 4 tau naught by rho u square by 2, which is equal to 0.363164 by RE power 1 by 4. This is equation number 25. And the condition for Reynolds number is it should be in turbulent flow, 10 power 5. This is for turbulent flow through a smooth round pipe. Okay. And then we have Lee's empirical friction factor, Lee's empirical equation for friction factor. So different scientists propose empirical relations based on their observations by changing different set of equations or different set of parameters. Okay, they have come up with different empirical equations. So in 1924, Lee has also developed a correlation for friction factor in turbulent flow for a smooth round pipe, and this was based on his experimental work. Okay, so empirical equations always will have a certain error in them, right? So that is why many scientists were able to come up with different equations. Okay, so F will be equal to 4 tau naught by rho u bar square by 2. So this will be equal to 0.0072 plus 0.611 by RE power 0.35. This is based on his observations. And here uh, RE varies between 4000 to 4 into 10 power 5. So this is again for turbulent flow in smooth round pipe. Okay. Then we have Schiller and Hermann empirical equation for friction factor. Okay. So in 1930, again, scientists, both the scientists, Schiller and Hermann, so they suggested again new empirical correlation based on their experimental work. This is again to estimate friction factor in a turbulent flow through smooth round pipe. So according to their observation, F will be equal to 0.0054 plus 0.396 by RE power zero point 0.3. So this is equation number 27. This is again for turbulent flow in smooth round pipe. So they also did this experiment using these conditions, that is RE should be between 2300 to 4 into 10 power 5. Okay, that is in turbulent region. And we have one more scientist, he could say empirical for friction factor. So in 1932, he developed an empirical correlation again based on his work, and for the same condition, that is turbulent flow through smooth round pipe. So according to his observations, F will be equal to 4 tau naught by rho u bar square by 2. So this is according to his observation, that is 0.0032 plus 0.221 by RE power 0.237. So this is equation number 28. Again, turbulent flow in smooth round pipe. So the conditions for Reynolds number is as follows: 10 power 5 less than RE less than 10 power 8. And then we have one more scientist, that is Moody. So in 1944, Moody, he again, based on his experimental work, developed the empirical relation, but this time this is for a rough pipe. Okay, so according to his observations, F is equal to 4 tau naught by rho u bar square by 2. So this is equal to 0.0055 into 1 plus 200, sorry, 20,000 into 2 epsilon by d plus 10 power 6 by Re power 1 by 3. This is equation number 29. And this is for turbulent flow through rough pipe, rough round pipe. So the conditions for Re are 4000 less than Re less than or equal to 10 power 7, and they also did the experiment for epsilon by d, which is between 0 to zero point 0.01. Okay. And for transition region, Descoy and L. They proposed a empirical equation. So friction factor for transition. Okay, so this was proposed in 1989, and according to them, F is equal to zero point 0.5 into 0.0112 plus 1 by R e power 0.3185. This is equation 30. And this equation is only for written in fluids. Okay, so this is the condition for Re. So this falls under transition zone. So what are the factors? So we were going through different empirical formulas proposed by different scientists based on their observations, right? So, but what are the factors which might be affecting? So if you want to develop an equation, let's say in future, so what would be the factors that we'll be considering into so that will be affecting this head loss? Okay, factors that affect head loss. So what are the factors that would be affecting? So what is the formula for HF? HF is Ft into L U square by D H into 2G. Okay. So it is clear that flow rate is one parameter which affects. So flow rate and diameter is also a quantity, or you can say inner diameter to be specific, inner diameter of pipe, and roughness will also be. So if it is more, if the surface is more rough, it will be having more effect on the head loss rate. So roughness and length also affects, right? Length of the pipe. Okay. What else? Viscosity of the fluid will also be affecting. Viscosity of the fluid or liquid. Then what will be the other parameters? Fluid is done in diameter Roughness of the pipe, length of the pipe, viscosity. What else will be affecting? Corrosion will also be affecting it. Corrosion and scale deposition. So corrosion and scale deposits. And fittings will also be affecting. If there are more fittings, there will be more loss, right? And also tightness of the pipe. Okay. So these are the different parameters which will be affecting or influencing the head loss. Okay. So these head losses can be classified into two types, that is major head losses and minor head losses. So let's check them. Major and minor losses. Okay. So major losses are due to the fluid friction in a normal geometric pipe, and whereas minor losses are due to the fluid friction in geometric change of pipes. Okay. So whenever there is a change in the geometry, those losses are considered as minor losses, and the normal friction losses in a normal geometry pipe are considered as major losses. So HF major can be written as FD into L by DH into U square by 2G. So where FD is Darcy friction factor. Okay, and we have minor losses, that is given by HF minor is equal to K into U square by 2G, where K is minor loss coefficient. Okay, so is there any way that we can find out an equivalent length so that minor losses will become equal to major losses? So for that you just have to equate both the equations. Or we can do one more thing better. So FD into LE, that is equivalent length, into DH is equal to K. Okay. So LE will be equal to DH by FD into K. So this gives relation between length of the pipe for which both minor loss and major loss will be equal. Okay. So whenever, as we discussed, whenever the geometry of the pipe changes, there will be losses will be increasing, right? So let's say instead of a circular pipe, we are having a rectangular conduct or rectangular um pipe, and then we have something which is having an oval shape. Okay, something like this. So how do you calculate losses in such pipes? So you have to consider something called hydraulic diameter. Okay, so same thing, everything remains the same. Okay, so but when you are taking diameter of the pipe, instead of taking diameter directly, you have to take hydraulic diameter. Okay, so how do you calculate hydraulic diameter? Hydraulic diameter is given as DH, that is cross sectional area by wall perimeter in contact with fluid. Okay, this is 4 into cross section area by wall perimeter in contact with the fluid. Okay, so let's take the case of square or rectangular pipe. So what would be the area? Length into breadth, right? And what will be the wall perimeter in contact with the fluid? That will be so, or you can also say it is weighted wall perimeter. Okay, so wherever you have to just find out the perimeter where a fluid is touching the surface of the wall. So here it will be equal to the normal perimeter because it will be touching all the four walls. So it will be 2 into L plus B. Okay, so DH will be equal to 2LB by L plus B. Okay, and if you take a square pipe, okay, or square cross-sectional pipe, so here DH will be 4 into area is A square by what will be the contact or wall perimeter or weighted wall perimeter, that will be 4 into A, right? So DH will be equal to A for square pipe. Okay, so this is how you'll be able to calculate loss in a pipe. So you have to consider hydraulic diameter. Okay, so then we have minor head loss due to additional turbulence. Okay, so in a pipeline, head loss is also produced because of additional turbulence, which arises components where because of components which causes a change of area. Okay, and because of junctions, because of bends, change in direction of flow, branching. So these parameters will also be causing additional losses. Okay, so that is because of change of area. So this could be either sudden and gradual as well. And because of junctions, change of direction of fluid or change of direction of fluid motion, because of bends, branching, valves. Okay, so there are many other reasons which will be causing additional losses. So generalized equation for accounting all such head losses can be given by H area, that is additional head losses will be K into U square by 2G. Okay, where K is a coefficient which depends upon the geometry and direction of flow. Depends on geometry and direction of flow. Okay, so this is a loss factor. So let's consider cases with sudden expansion. So loss of head due to sudden flow expansion. Okay, so let's say a pipeline is connected to a tank, or you're filling a tank with, or a reservoir. You're connecting a reservoir, you're filling a reservoir using a pipeline. Okay, so initially area was let's say A1. This is A1, and now this is flowing. This is having a sudden expansion. So this is already filled, and this is suddenly having a more area. Okay, so this sudden change in area will also cause head loss, and this is given by head loss due to sudden expansion, that is given by change in velocity, that is u1 minus u2 square by 2g. This can also be written as 1 minus a1 by a2 whole square into u1 square by 2g. Or simply you can write h expansion is equal to ke into u1 square by 2g, and here ke is 1 minus a1 by a2 whole square. Okay, so if in this case, if the expanded cross-section area leads to infinity, that means if the water is flowing into a large reservoir, okay, so where the area will be infinite, that means very high, very large when compared to this small pipe. Okay, in that case, K tends to unity, and the loss in that case is called exit loss. Okay, only this is applicable only when the reservoir is of very large area when compared to the pipe area. Okay, so it's called exit loss. And this we have one more case that is loss with change of area. This is sudden flow contraction. Okay, so we have a larger pipe, and then we have a smaller pipe. Okay, so initially it was having a velocity of let's say u1, and the cross section area is a1, and now suddenly it is flowing in a smaller channel. Okay, and there will be sudden contraction as well, right? So there will be sudden contraction, and the velocity will be reduced. So it won't directly, take this shape. First, it has to, overcome this obstruction. Then it will be flowing something like this. Okay, so there will be this contraction. Okay, so here it will be having U, C, and then it will be finally it will be having U2, that is velocity in the normal channel. Okay, so this loss, this sudden change in or sudden contraction will cause loss in the velocity, or change or loss in the head, which can be calculated as H contraction will be equal to UC minus U2 by, instead of changing from U1 to U2 directly, it will first change from U1 to UC, and then it will change to U2. Okay, because of the suppression zone, or because of the sudden contraction. Okay, so UC by U2 by 2G, which is whole square. This will be equal to A2 minus A2 by A1 minus 1 whole square into U2 square by 2G. Okay, so this can also be written as 1 by KE minus 1 whole square into U2 square by 2G. So here KC can be written as AC by A2. Okay, and KC is called contraction coefficient, and A is generally, or sorry, AC is generally 61% of A2. That is final area. It will be almost 61% of A2. Okay, And there are two terms here. Uh, so whenever the fluid is flowing, fluid is getting contracted here. So it will first contract into a zone, and then it will occupy the entire pipeline, right? So let's say this length, the separation zone length is IC, and the diameter is DC. Okay. So this is a case valid only for IC less than DC. Okay. We have other cases as well. So what if IC is greater than AC? So IC greater than DC. Case IC greater than DC. Okay. So same thing, everything remains the same. So this is called the length of the narrow section is long compared to the diameter. Okay. So okay. So this is the length, that is IC, and this is DC. So here IC is greater than DC. So here the length of this narrow channel is long when compared with the diameter of the channel. Okay. So this device is called choke. Okay, because it is choking the fluid, right? So this is called choke, and head loss can be calculated as H choke is equal to K choke into U square by 2G, UC square by 2G. So that will be K choke into that will be Kc into A2 by AC whole square into UC square by 2G. Okay. So this can also be written as, so K choke can be written as Kc square into 1 by Kc minus 1 whole square. Okay. And Kc is AC by K2. Okay. So K choke is a choke contraction coefficient. Okay. And there's something called choke number as well. So the choke coefficient, that is K choke, that is choke contraction coefficient. So this can be expressed by choke number as K choke is equal to 1.16 plus 6.25 by N C power 0.61 whole square. This is if entrance is rounded, and if entrance is not rounded, K choke will be 1 plus 5.3 by NC power zero point 0.5 whole power 2. This is if entrance is not rounded. So choke number is defined by NC is determined by Q by U bar into LC, where LC is the characteristic length and U bar is the mean flow velocity in the pipe. Okay. So we have different conditions for KC. Okay. So let's look at them. So if this contraction is very sharp, Okay, if this is round edges are sharp, or if the entrance is very sharp, so in that case Kc will be zero point 0.5. Okay, and if this is a bit rounded, or if this is a bit smooth or rounded, okay, if this edge is rounded or entrance is rounded, in that case Kc is 0.25. And let's say if this is having a bend, something like this, which is not sharp, okay, this is a gradual change, then Kc can vary between zero point zero 0.06 to 0.005. Okay, so depending upon these different conditions, so we can have an angular channel, we can have, okay, different conditions. So based on that, Kc value will be changing. Okay, so we also have losses when there is a flow change as well, direction of flow change as well. Okay, so it's basically is a conceptual and more of a theoretical thing. Like we have many predetermined values. Okay, so I won't be going through that. It was already discussed in the class by professors. But if you have any doubts, you can ask me. Okay, I'll try to answer them. And also, sir also discussed about head loss in pipe branches as well. So whenever there's a pipe branch or a junction, okay, even then there will be losses, right? So we just discussed that. Whenever there is a branching, whenever there is a wall, whenever there is a bend, okay, or whenever there's a change of direction, we will be having losses, right? Head loss, right? So Professor Majumdar sir has already discussed these things. So if you have any doubts, I'll try to explain them. If not, we'll be moving on to problem session. Okay. If you have any doubts, please let me know. You can type them in the chat box, or maybe unmute yourself and ask me. Any doubts? Okay, so I hope that you're not having any doubts. Okay, so let's move on to the problem session. So coming to first question, in turbulent flow, losses are proportional to viscosity as. So how is this related? So for turbulent flow, losses will be proportional to its proportional to square of the viscosity. Okay. Coming to second question, the fanning friction factor for a laminar flow through a circular pipe is given by. So what is the formula for fanning friction factor? We already discussed this. What is the formula? Laminar flow through a circular pipe. FF will be 16 by rho u bar d by mu, right? Which is equal to 16 by RE, right? And if you want for Darcy friction factor, FD will be equal to 4 times of FF, which is equal to 4 into 16 by RE, which is equal to 64 by RE, right? So this is only for laminar flow through a circular pipe. Okay. So coming to third question, what is the fanning friction factor if RE is 1600? What would be the fanning friction factor if RE is 1600? So if it is 1600, that means RE is less than 2300, or if RE is equal to 1600, that means it is a laminar flow rate. So in a laminar flow, fanning friction factor will be equal to 16 by RE, right? So if you substitute it here, 16 by 1600, which will be equal to 0.01, right? That will be option C. Okay. Coming to fourth question, the loss of head due to bends in a pipe depends upon. Loss of head due to bends in a pipe depends upon all the above. So loss of head due to bends in a pipe depends upon which of these? It will depend upon all the above. Hmm, this won't be there. Okay, that will be option B. Okay. Coming to fifth question, which of the following does not cause head loss? Branching, friction, velocity change, bend. So which of these following will not cause head loss? That will be option C, velocity change. Okay. Flow rate change will cause head loss, but velocity change will not be causing head loss. Okay. Head loss in a branch pipe can be varied with branch angle, diameter ratio, discharge ratio, D, all the above. What is the again conceptual question which was discussed by professor in the class or in the tutorial? So that will be option D, all the above. Okay. So if you have any doubts in this, you can ask me, or if not, we can end this session. Okay. Any doubts? Okay. So if you don't have any doubts in either the problem session or in the tutorial part, we can end this session. So thank you everyone. Thank you for attending the session. Let's meet on next Tuesday, same timing. Thank you.